Hello, Math 200 students. This is looking at section 6.3. Again, chapter 6 is about confidence intervals, and 6.1 was a confidence interval for a population mean when the population standard deviation is known. 6.2 was about a confidence interval for a population mean when the population standard deviation is not known. This is a confidence interval for a population proportion. So, like if we want to say what percent of the population likes bacon, we might say 85% of the population likes bacon. And now we're looking at a population proportion. So if our hypothesis is that 85% of the population likes bacon, we're likely to be wrong. I mean, we're almost certain to be wrong on that. But if we do a sample and we get that 85% of the population of that sample likes bacon, then we're going to form a confidence interval around that. It's going to grow, right? It's not going to be 85% on the dot. It's going to be like, well, between 82 and 88% of the population with 95% confidence. We will say that between 82 and 85% of the population likes bacon. Something like that. So let's go on with the chapter after that introduction. Recall from section 4.2 that the probability of success for a single trial of a binomial experiment is P. The probability is a population proportion. In this section, you will learn how to estimate a population proportion P using a confidence interval. As with confidence intervals for mu, you will start with a point estimate. The point estimate for P, the population proportion of successes, is given by the proportion of successes in a sample and is denoted by P hat. This is called P hat. Little triangle thing above the P equals X over N, where X is the number of successes in the sample and N is the sample size. So if I interview 100 people and 85 of those people like bacon, then X would be 85, N would be 100, and P hat would be 85 over 100, or 0.85, or 85%. Another example might be if I take 50 shots at a free throw, and I make 27 of those shots, then X is 27, and N is 50. All right. The point estimate for the population proportion of failures is Q hat, which is the complement of P hat. So 1 minus P hat. In other words, Q hat for the bacon example would be 15% didn't like bacon. Or for the free throw example, I guess it would be, what would that be, 23 misses and 27 makes, and that comes out to 50 total, right? Okay, example 1. Finding a point estimate for P. In a survey of 1,000 U.S. teens, 372 said that they own smartphones. I bet this is very dated. It'd be a lot more than that now, wouldn't it? Find the point estimate for the population proportion of U.S. teens who own smartphones. Well, that would be pretty darn easy. 372 out of 1,000, or 0.372, or 37.2%. All right, that is extremely simple, hopefully. Next page. All right. Constructing a confidence interval for a population proportion is similar to constructing a confidence interval for a population mean. You start with a point estimate and calculate a margin of error. So a C confidence interval for our population proportion P, so C confidence would be like 90% confidence, or 95%, or 99%, or whatever it might be. And the margin of error is going to be Z sub C. That we find that the same way we did before with the inverse normal on our function on our calculator, times the square root of P hat times Q hat divided by N, where N is the sample size. The probability that the confidence interval contains P is C, assuming that the estimation process is repeated a large number of times. All right. In section 5.5, you learned that a binomial distribution can be approximated by a normal distribution when NP is greater than or equal to 5 and NQ is greater than or equal to 5 as well. and the sampling proportion of p hat is approximately normal with a mean of that and a standard error of that. So the mean, we're going to, in other words, we're going to, as long as we have more than 5, as long as the n times p, so let's say n is 50 and the 50 shots, and the proportion, the probability that I make a shot is 60%, then 50 times 0.6, as long as that's greater than or equal to 5. And I also have to do n times q. So like if the probability that I make a shot is 60%, then 50 shots, n would be 50, q would be 0.4 instead of 0.6. And that would also need to be greater than or equal to 5. When those two things are the case, then I'm going to do these techniques that we're describing here. In other words, you can treat the binomial distribution. It's going to act like a normal distribution when those conditions are met. The mean of that is going to be p. All right. In other words, the mean u for the proportion would be the probability that I make a shot, any shot in a binomial experiment. So in this case, it would be 60% according to what I just told you earlier. To get the standard error, or I guess it's kind of like standard deviation, you do this formula. The square root of, in the case I just told you, it would be 0.6 for p, 0.4 for q, over 50 shots for n. Okay. Feel free to pause this and read these guidelines as a summary of what to do. As I have told you earlier, you can also, there's also going to be an easier way to do this in the calculator, just like there was an easier way for the confidence intervals that we did in 6.1 and 6.2 for the mean. All right, use the data in example 1 to construct a 95% confidence interval for the population proportion of U.S. teens who are on smartphones. All right, we got to remember what that data was. So 372 out of 1,000. So we're going to go to our calculator. Well, one way to do it is to do it kind of the long, detailed way, where we find this margin of error by finding z sub c by doing the inverse normal for that, and then doing this formula here to get the margin of error, which they get to be about 0.03. And so then they take the point estimate, which was 372 out of 1,000, or 0.372, and they add 0.03 to it, and they take 0.03 away from it, and they construct this this 95% confidence interval based on that. But we can do that in an easier way by going to the calculator, and we're going to go to, I got to remember this is always kind of a trick to remember. I think you go to stat, then you go to tests, and we want to go to, I believe it's going to be one prop z-test. One proportion z-test, I believe, is the correct thing to do here. So one proportion z-test. And I think I just told you wrong. It's not the one prop z-test. If you keep going down, it's not a z-test, it's a z-interval. So it's this option right here, the letter A here. One prop z-interval. We don't want a z-test, we want a z-interval. One prop z-interval, one proportion z-interval. All right, x is the number of successes in our sample, so that would be 372 in this case. And n would be the number of trials in our sample, that would be 1,000 in this case. And the confidence interval we want, the confidence level we want is 0.95 according to what we're told in the question. And so we just hit calculate, and that gives us our confidence interval. That's just really simple. So that's a good simple way to do it. And if you want to get the margin of error, you could do the formula that I just spoke of a little earlier in the video, or you could go ahead and do the confidence interval and get the margin of error from there, as I've told you in earlier videos. You can do that by subtracting either one of the endpoints of this confidence interval from the mean. All right, if you subtract the mean from this, you're going to get the right answer, or if you subtract this from the mean, you're going to get the right answer for the margin of error. Or another way to do it is to take the difference between the two endpoints. You can do the upper limit here, 0.402, and subtract the lower limit here, 0.342, and then cut that in half, cut that difference in half, in other words, divide it by 2, and that will also give you the exact same margin of error, which would also be the correct way to do it. All right, so interpretation, that means we can say with 95% confidence, you can say that the population proportion of U.S. teens who own smartphones is between 34.2% and 40.2% based on our sample that we hypothetically did there. The confidence level of 95% used in example 2 is typical of opinion polls. The result, however, is usually not stated as a confidence interval. Instead, the result of example 2 would be stated as shown. A survey found that 37.2% of U.S. teens own smartphones. The margin error for the survey is plus or minus 3%. So I guess when it gives you that kind of a statement, the assumption is that it's a 95% confidence level because that's the most common confidence level. It doesn't mean that has to be the confidence level. You could do more or less than that. Moving on to the next page. The figure at the right is from a survey of 498 U.S. adults. Construct a 99% confidence interval for the population proportion of U.S. adults who think that teenagers are the more dangerous drivers. All right, so we know that the number of trials or the size of the sample is going to be 498 because that was the survey. And we have 71% of those 498 said that they thought teenagers were the more dangerous drivers. So we go to our calculator and we go to stat and we do the tests and we go all the way down to one proportion z interval, one prop z int. And for x, it doesn't explicitly give me the number of people who said that, but it tells me 71% of 498. So I'm just going to type in 498 times 0.71, and that will be how many of that 498 said yes. And then, so 353 let me make sure 33.58 wasn't 498, yeah. And then n is going to be 498. That's how many were in my sample. My confidence interval, my confidence level was what in this problem? 99%. So 0.99, and then hit calculate. I think it won't let me do. I think the reason we got an error there, I believe, is because we put in a decimal. So we're going to need to round that. So instead of 3.58, let's just put 354. And calculate that. Now it gives it to me. So 0.658 all the way to 0.763. So to be 99% confident about the mean, about the proportion, we need to say that the proportion is somewhere, but with 99% confidence, we can say that the proportion of the population that believe that teenagers are the more dangerous drivers is between 66% and 76%. All right. Moving on. Next page. Finding a minimum sample size. One way to increase the precision of a confidence interval without decreasing the level of confidence is to increase the sample size. Given a C confidence level and a margin of error E, the minimum sample size needed to estimate the population proportion P is this formula right here. This is just, again, doing some algebra on the formulas we were given before to get in by itself and using this formula. This formula assumes that you have preliminary estimates of P hat and Q hat. If you don't have preliminary estimates, then you're going to have to just use 0.5 for P hat, both P hat and Q hat. So 0.5 there and 0.5 there in your formula if you don't have those preliminary estimates. So let's do example 4. You are running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the population proportion. That sentence right there gives me the margin of error, E, in the formula. So the margin of error, E, will be 0.03. Find the minimum sample size needed when 1, no preliminary estimate is available, and 2, a preliminary estimate gives p hat equals 0.31. Compare your results. So when no preliminary estimate is available, that means we use what for p hat and q hat? We use 0.5 and 0.5. So I do the formula, and I put 0.5 in for p hat, and I put 0.5 in for q hat. The z sub c, you can get that in your calculator if you want to know a 95% confidence interval for z sub c. Z sub 0.95, in other words, you go to second distributions and go to inverse normal. This is something we've said before. You can either do a left tail or a center if you're able. If we were doing a left tail, we would do 0.025 for the area. Since we have the ability to do the center, I'm going to put 0.95 for the area. And just do the center instead of a left tail. And that should give me my z sub c that I need. Yeah, negative 1.96 and positive 1.96. And all you care about is just the positive 1.96. That is the z sub c we need. And we already said the margin of error is 0.03. You stick all that in the formula, and you get that you need n to be at least 1067.11. In other words, and you're always going to round this up to the nearest whole number because you can't get 0.11 of a person in your survey. And so you need to, it's better to be above than below in your sample size to get the precision you need. So we're always going to round that up. So we would say we need at least 1,068 people in our poll or in our survey to get that precision and confidence level that we need for our estimate. All right. Part 2 is it says do this again when we have a preliminary estimate of p hat to be 0.31. All right. So we're saying the proportion of registered voters who will vote for our candidate, we're estimating that to be 31% of the registered voters. Somehow there will be some initial way to figure that out, is the assumption. So we do the formula again. Everything's the same except p hat is 0.31 and q hat is 1 minus 0.31 or 0.69. And then we go ahead and fill in the others the same way. And we get that if that's the case, we only need 913.02. So we're going to say we only need 914 people in our survey. All right. So that does it for section 6.3. I hope that you found that to be pretty simple and that you're getting a good hang of everything in chapter 6. Good luck on assignment 6.3, and I may see you again in chapter 7 if we have a little time to cover some of chapter 7 before the end of the quarter.